Professor Bindu and Konishi-san, can you hear me?
Yes.
Okay. Please check your screen sharing.
Can you see?
Okay. Yeah.
Okay, good.
This is not presentation mode.
Okay. Okay.
Okay. Thank you. Konishi-san, can you?
Yeah, I'm sorry. My mic was off.
Oh.
Yeah, I'm back.
Can you share your screen?
Oh, sure. Can you see my screen? It's in presentation mode.
Okay.
Okay, thank you.
Professor Bindu, first I will introduce you, and then every member is introduced. Please, your camera on, and we will share your face on the whole. So then please do it. Thank you. It's okay. It's okay. Thank you. And then I will ask you to camera on in presentation in and then please. time to start our企画session. Hello, Jsai, hello, Kumamoto. This企画session is on the recent trends in open world continuous learning. This topic is related to AI autonomy that incrementally learns tasks from open world. And today, there will be the leading researchers presentation. And this speaker is written here. Let me introduce today's timeline. First, start from invited talks from, as I mentioned, leading researchers on this field. First, Professor Bin Liu presents an overview of continuous learning and directions of the open world continuous learning. Today's topic, today's main topic, and then three leading researchers present their activity and their thinking future direction. First is Wataru Kumagai from Tokyo University, and Ryo Karakida from AIST, and then Tatsuya Konishi and KDDI Research. And facilitator is me and Mori Kurokawa from KDDI Research. And after the invited talks, move on to the panel discussion, and made by all presenters, all invited presenters. Now let me briefly introduce each presenter. First, Professor Bin Liu is a distinguished professor of computer science at the USC, University of Illinois at Chicago. He received test of time hours from two from KDD and one from Wisdom. And he is also the recipient of KDD Innovation Award. And he has also authored 4 books. One is related to today's topic, lifelong machine learning, and other topics related to sentiment analysis or web mining. And he appeared on the New York Times front page, and also on professional services. He has served as the chair of KDD from 2013 and 2017, and he made activation on various conferences. And then this is Wataru Kumagai. Wataru Kumagai is assistant professor of University of Tokyo. His research interests include artificial general intelligence and automated research and continuous learning. He has published extensively in top conferences, for example, NeurIPS. And the third is Dr. Ryo Karakida. Ryo Karakida was in the University of Tokyo and then the graduate school of University of Tokyo. And then from 2017, he is working on the AIST. And his research interest includes learning dynamics in neural networks, especially from theoretical perspectives. And the fourth presenter is Tatsuya Konishi. He was working on location-based machine learning or irregularly prediction during being a student. And then after joining KDDI Research in 2018, he studied a new direction of research in which machine learning, especially graph neural network and behavior change. And then now he is visiting Professor Bin Liu's laboratories in UIC, and he's working on continuous learning and achieve the forgetting prevention and the knowledge transfer. And his paper is accepted in PAKDT and also the ICML 2023. And again, so now all presenters, please make your camera on, and can you? I will switch off the sharing, and so this is our presenters. And me, Mariko Kawa. Sorry. Wataru Kumagai. Real character, please share your camera. Sorry. It's dark in this hole, so cannot see Wataru Kumagai's face. But afterwards, we will make part of discussion, and he will move to the stage. So and then I will introduce your face, his face. And this is today's presenter. And so we move on to the invited talk sessions. First, from the Professor Bin Liu, he will present continual learning and open world continual learning. So please start your presentation, Professor, please.
I can't start sharing. Well, some participants are sharing. Somebody else is sharing. Oh,
I stopped.
Okay. Still on. Okay. All right. All right. Thanks for the introduction, and also thanks for the invitation. And today I'm going to present this particular topic, which is pretty new, and not lots of research has been done, but some sort of initial work has been going on for quite a while, and it's very challenging. And so we focus on AI autonomy. We want to make system sort of autonomous. So one of the major techniques which we need to do is basically a major problem to solve is open world continual learning. Sometimes people just call it open world learning because open world learning by nature is continuous. So let's start with traditional machine learning, and which we call the isolated single task learning. And we have a task T, and then we have a data set, so labeled data set D, and then we have a machine learning algorithm that produces a model, and the model goes to application. So this is just like a waterfall. So there are many weaknesses for this type of classic machine learning paradigm, and today we are going to focus mainly on these three. The first one is the traditional machine learning does not have continual learning. So there's no knowledge accumulation and there's no knowledge transfer. And the second one, there's no learning after deployment. So which basically say the model is fixed after deployment and there's nothing you can do and when you are using the model. So this is not suitable for open world learning. And with this sort of paradigm, we have an assumption which is called a closed world assumption. So it basically says in the application or in the deployment, that's nothing new, that's nothing novel. Basically, you just apply to the problem. But in real life, the world is dynamic, and when we learn something, we always see something new when we apply what we have learned. It's just like we in school, the students in school, they learn something, but when they go to work, and obviously they will see something new, they have to sort of learn continuously. So in this case, we're talking about we have to detect novelties, detect things we don't know, and then learn those things. And this process, of course, is continuous, and then becomes more and more powerful and more knowledgeable. So formally, we're talking about closed world assumption basically means that the classes during testing, which may appear in the testing, should be a subset of training, which basically says whatever you're seeing in testing should have been seen in training. So there's nothing new. Okay, this is the closed world assumption, which is basically applied in many applications in real life. Of course, in those cases are narrow sort of application domains. In the real world, and we have this sort of dynamic situation. We have the open world setting, and then we have novelties. We have unseen stuff. We have unknown stuff. We just say that the classes appeared in test. Some of those classes appeared in test may not have appeared in training. So that's something new we need to detect, and then we also need to learn them. I also want to say a system unable to detect anything new cannot learn by itself. So you cannot be autonomous. So open world learning is essentially continuous. And in terms of learning itself, it mainly talk about out of distribution detection, and which essentially try to detect novelties. Sometimes we'll call it anomalies, open world recognition. There's many names for this. And next one, after you detect this new items or new objects, and then we need to incrementally learn it. That's continuing learning, sometimes also called lifelong learning. So in order to achieve autonomy, we need to get this thing done. Of course, these two are not enough. Also, we call this two open world continual learning, but there's also another sort of major part, which is called adaptation. And adaptation is the one which has not been sort of explored much, but it's extremely challenging, as we'll see later. So I just give you a practical sort of also personal experience with self-driving. I consulted for self-driving car company several years ago, and once we took the car out for a road test, and basically we go to a place which is pretty quiet. There are some cars, but not many. And once at the one moment, and this at a particular T-junction, this car suddenly stopped and refused to move, basically complete stop. And we can't do anything, and then the car just does not want to move. And we look at the front, and look at the front, the back, and the left and the right, nothing. Everything is clear, and there's nothing on the road. So we have to sort of manually take over and drove the car back to the lab and do some sort of debugging. And what we found was one of the sensors detected a pebble on the road. It's a very small stone. As the human eyes, you don't really notice because the road is kind of messy, right? That's sort of small pieces of things you can see. And then we didn't really notice anything, but the car just stopped. If we imagine and the car can communicate with passenger or with the engineer, just say, I detect unknown object, and what should I do? And then of course, as engineers, we were in the car, we could just say, safe, just go ahead. So this is essentially a kind of interaction with people. The agents, the car's agent interacts with people at the same time, and get the instructions and learn to recognize this kind of objects, and also to learn in this situation it is safe, and you can go ahead without stopping. So this is something what we call the learning on the job or learning on the fly. This is very typical of open world learning. Open world learning is on the fly. I want to see something and then we learn it. Can learn it. So if we can achieve this, that would be really, really interesting. Really interesting. So in order to achieve that, let's talk about the continuing learning first. So continuing learning or lifelong learning, as it was called many years ago, essentially try to learn a sequence of tasks. And you have T1, T2, Tn, and it can be indefinitely and incrementally. Each task in the supervised learning setting essentially consists of a bunch of data points with classes, and then we basically have to learn this task. So each task consists of a set of classes to be learned. So our objective are twofold. The first one, we want to deal with catastrophic forgetting, which basically means when we learn the n+1 task, and we have really learned the first n task. So when we learn the first n task, we basically pretty much fix the neural nets sort of parameters, right? But when we learn the n+1 task, obviously we have to change the parameters in order to learn the new thing, because this thing has not been seen before. And then in order to learn this thing, you have to modify some of the weights or some of the parameters in the network. That causes problem for the previous task. So for example, you can have sort of accuracy degradation, and which is not good. So we want to keep the previous task perform at the level when they were learned. So we don't want anything get forgotten. Okay. The second objective is to do knowledge transfer. So we want to leverage the knowledge learned in the past to learn a new task in order to learn better, or probably to learn more efficiently. So there are two assumptions, okay, two major assumptions which I'm going to deal with. The first assumption is that once a task is learned, the data is no longer accessible. So at least most part of it. So this is pretty much the same as with humans, right? When we learn to recognize apples, or learn to recognize bananas, yesterday and then today, when we learn sort of another fruit, for example, pineapple, and we don't really sort of get the data from the yesterday and all those images. We have recorded those images from yesterday, and now we learn this pineapple. Of course, you can imagine saying, yeah, it's possible. I can remember what we learned yesterday. Those there's 2 apples I saw, and there's sort of a banana I saw. But if you think about this in tens of thousands of tasks, tens of thousands of sort of objects you need to learn, then there's no way you can do that. Okay, there's no way you can do that. So that's the problem we have to deal with. So you have to do it incrementally. The second one is the task and the training data are given. So in this particular setting of traditional continuing learning or lifelong learning, we assume the task and the training data are given. However, in the open world, these are not given, because you as an agent, you face the real world and work in the real world, do your performance task, and then you have to detect something which is unfamiliar or is new, and then you got to learn by yourself. So that's basically transition to open world continuing learning. So schematically, we can see this sort of diagram. We have a set of tasks. We have sequence tasks with T1, T2, Tn, and T+1. This is the new task. Now we have the Dn+1, which is the training data. And then we goes to this machine learning algorithm, this is the continuing learner. And if we have previous knowledge accumulated, and we can somehow exploit that knowledge to make this model better, to learn a better model or to learn more efficiently. And then this goes to application. So this is the traditional setting. Obviously, this is not suitable for open world because this is not a closed loop. Okay, it's not a closed loop. So in order to talk a little bit about a theory about this open world learning, or it's a continuing learning, and we need to have some concept ready. So the first one we want to talk about is the setting of it's one of those popular settings of continuing learning, which is called task incremental learning. So in this case, the problem is fairly simple. You just say we want to learn a model, a separate model for each task in a neural network. Okay, and the test time and the task ID is provided for each test instance. Okay, so for example, we have a task 1, we learn to recognize different breeds of dog. So you're saying different breeds of dog are basically class labels. So in the task 2, we learn to recognize different kinds of animals. And task 3, we learn to recognize different type of fish. So you may notice these 3 tasks have some kind of intersections. For example, different animals could include dogs, could include fish. But in the task 1, the task 2, task 3, we want to be more fine-grained. Okay, want to be fine-grained. So in this case, you can see when we present a picture or the image for the system to recognize, the system must know which task you want to perform. Do you want, for example, provide a dog? Do you want to classify this as a sort of a particular species or particular breeds of dog, or are you just tell me this is a dog? It's a kind of animal, the dog itself. Okay. So in this case, we need task ID. So the formal definition is at the bottom. So the only thing we need to notice is this f functions, this sort of a classification function need to take the input of x. This is the input data plus the task ID, which give us the class label, the y class label. So you can see this is a sort of different from the traditional supervised learning because we have this T attached because we have different tasks. Okay, so this problem is fairly easy to solve in terms of catastrophic forgetting. Okay, of course, knowledge transfer will be a different issue. All right. So this is the second sort of setting, which basically says we want to learn classes incrementally. Okay, and this problem is very, very challenging, and this is basically connected to open world learning. Okay, so for example, we learn to recognize pig. So it's task 1, we recognize pig and cat. And task 2 is sheep, and task 3 is chicken and dog, and task 4 is horses and the cows. So you just basically imagine the day 1, I saw some pigs and a cat, and people tell me, oh, this is a pig and this is a cat. I learn to recognize them. The second day, I see another animal. So somebody say this is a sheep, and then I learn to recognize sheep. The third day, I learn this thing. So in this case, we are building a single model instead of building multiple models like in the task incremental learning. So we build a single model in this case. So when I present an animal, for example, a dog, and you tell me it's a dog, okay, no task ID provided. Okay, there's no task ID provided. You can see the red box at the bottom. I should say you can see that X, okay, maps to Y. So instead of X cross T maps to Y. Okay, so these two problems are different, and the second problem is much more challenging. So this problem, why this problem is very challenging? The problem is because this guy has an additional issue which we need to deal with. So previously we talked about forgetting, we talk about sort of knowledge transfer, but in this case we have another major problem. This is a bigger problem than, I think it's a bigger problem than the previous two problems. So we call this problem for the inter-task class separation. I'll sort of in a short form IC, which is very hard to deal with. So what is the problem? The problem is, you remember we say when after task is learned, data is no longer accessible. Okay, so for example, we learn to recognize this bunch of animals. Okay, this bunch of animals. So now at the day number 4, and which is task 4, let's say we talk about task 4, we learn the horse and the cows. But at this moment, at day 4, we don't have the data for pigs and cats, cats and the sheep and the chickens and the dogs. We don't have those data anymore. So now you will learn only horse and cow. But we still need to establish the decision boundary between horse and the pig, horse and the cats, horse and the sheep, horse and chicken, horse and dog. But we can't do it. The reason is we don't have the data for the previous, previous animal anymore. So that's a big problem. Okay, if you don't establish a good decision boundary, then your classification is going to be very bad. So the same thing for the cow. I mean, cow also has to have a decision boundary, and with the pigs and the cats and the sheep and the chicken and the dogs. So this is what we call inter-task. So it's the between task class separation, and this is the problem very difficult to deal with. And although there are some techniques to try to deal with this implicitly, they just say I save a little bit of data of the previous task, very little, okay, very little data. And then when I train the current task, I sort of use this previous data to help me to sort of deal with this forgetting problem and deal with the inter-task separation. So previously people just identify, say, this save the replay data, so the previous data is only for dealing with sort of forgetting. But the more difficult problem is the inter-task class separation, okay? So we need to understand this problem. If you understand this problem, then we can talk about the theory, and we can talk about what is the intuition behind the theory, okay, behind the theory. Well, as I just said, and the CIL, this class incremental learning, is closely connected to open world learning. So now we want to sort of have some theoretical result about the CIL. And in this case, we decompose this particular problem into two subproblems. The first one is, not the first one, the probability of X belongs to a particular task and a particular class within the task, and is on the left-hand side. So now on the right-hand side, you see the second line, and we have the first part, which we called within task prediction. The second part was called task ID prediction, okay, task prediction, all right? So how do we understand this probabilistically? So you can see the conditions, X belongs to a particular task, K is a task, and the 0, don't worry about 0, just say particular task, and just use the 0 to indicate a particular task. And then the X belongs to a particular task, a particular class, and what is the probability of that? So that's essentially say within the task, okay, within the task prediction. The second one says X belongs to a particular task. Obviously, this is task ID prediction. So if we go to see the example here, just say the first probability, you say, let's assume I know we are basically classified within the first task. So I give a picture, I say I'm going to predict within the first task. Then that's very easy. Okay, you learn these two animals, the pig and the cat. And the second probability is trying to say which task it is. Okay, I present the picture, let's say I will present chicken, and then you basically tell me, yeah, this comes from task 3. And then not task 1, not task 4, not task 2, but task 3. And then this is quite intuitive. Okay, it's quite intuitive. So it's a product of those two probabilities. So the theoretical result says the good WP and the TP, and don't worry about OD yet, are necessary and sufficient conditions for good CIL. So this is quite, if you just look at this equation, this decomposition, this is obvious. Okay, this is obvious. Of course, we need to prove it using, we will prove it using the cross entropy, those kind of in the deep learning framework. But the important part is the OOD detection. You can see this one, or OOD, out of distribution detection. So we prove also that task ID prediction is basically correlated with the out of distribution detection. Okay, and this is not difficult to see. Okay, it's not difficult to see because we want to predict task ID, and if you know if your OD is good, then this task ID should be fairly easy to predict, because when I give you a picture, then you know it does not belong to this task, does not belong to that task, then you must belong to one of those other tasks, right? This is quite intuitive. And what is interesting is also it's unified the CL and the out of distribution detection. You remember we said open world learning actually start with out of distribution detection, because we need to recognize what's new, right? What's new, what we have seen, this thing is new, and then we continue to learn it. So that is basically out of distribution detection, and the continue to learn that object is CIL. Okay, is CIL. So you can see this got this two unified, and the same this, and obviously the later on we'll see this also form the theory for open world continued learning. And then we also propose quite a few algorithms based on this particular theory. Okay, theory. So the intuition, what's the intuition of this theory? I just already mentioned that. And so the intuition is also quite simple. If we assume and the out of distribution detection is perfect, okay, then the CIL model basically solves the ICL's problem, and the CIL is reduced to WP. It is reduced WP. So let's see this example. Okay, so let's say for each of these tasks, we build an out of distribution detection model. What does that mean? That means if for this task one, if I present the picture, present the image, which is not a pig, is not a cat, I can detect it. Okay, and for task two, if it's not a sheep, I know it's not a sheep. And for task three, if it's not a chicken, it's not a dog, I know it. So that's out of distribution detection. So if you know, if you can do this out of distribution detection perfectly, just assume we can do it perfectly, then we know which task it is, right? I give an image, for example, chicken, you know it's not a pig, it's not a cat, it's not sheep, it's not a horse, it's not a cow. It basically does not belong to any of those three tasks. And we know basically belong to task number three. Okay, then if we know it's task number three, then we can do within task prediction, right? That's WP. So in this case, it's much easier, right? There's only two classes to be predicted. Then obviously to get the chicken is fairly simple. Okay, so you can see why this problem ICS is solved, because if you can do the task, you can do out of distribution detection, then you automatically have the separation of the classes within this task and the classes across different tasks, right? So that's why this problem got automatically solved. So below here is just the definition of out of distributed detection, which basically means you can see there's a classifier F, and there is the X mapped to the Y, which is the original set of classes, which we also call in-distribution classes. Okay, in-distribution class. The O is basically is a symbol representing the out of distribution. Okay, out of distribution. This is basically okay, we call it one class, but in reality, it can be multiple classes. Okay, multiple classes. That's the next problem. How do we deal with it? When we have a set of let's say images which we know are out of distribution. So how do we know they belong to the single sort of object or multiple objects? Okay, that's another area of research which we have been doing. So they basically try to clustering, basically try to clustering those data points to make sure you can form different class tables. But that problem is very difficult because the classes, when you assign object to different classes, they are actually very subjective. They are not objective, they're subjective, okay? For example, I'll give you different kind of dogs. If you see different kind of dogs, do you think they are all dogs? Or do you think this is a particular type of dog, this is another breed of dog? So it's very much sort of subjectively. Also, for example, you see the dogs and the wolf. I mean, you can say, okay, they're all dogs, or they're all the same. But if you want to fine-grained classify, you say, oh, they are different. So this is pretty much of a problem of have lots of subjectivities. Okay, so you can't expect the system itself to solve this problem. Of course, the system can solve this problem by itself in its own way, but that way may not be the same as the human's way. Okay, so in this case, we normally need human interactions in order to know what this new object is. Okay, so if the system itself, system may not be able to give a name. For example, you just give a serial number. This is the object number 15, for example, but I have no idea what the name of this object is. So anyway, let's come back and I will say, based on this theory, we designed quite a few algorithms. I'm just giving you one algorithm, and this algorithm essentially follows the theory. It says, I'm going to use a mechanism which allows me to do two things. First one is a within task prediction, and another one is the OD detection. So we are using a particular two algorithms, which are TIL algorithms, HAT and the SOUP. And as I mentioned earlier, we said that TIL, in terms of catastrophic forgetting, the problem is pretty much solved. Okay, basically means I can build TIL models, different model, one model for each task, and without forgetting. So there are many techniques. So here are two techniques. The first one is HAT. So what it does essentially says, I build a model for a particular task, for the first task, for example, and then I set some mask to protect those neurons which are important for this particular task. Okay, so when you learn the second task, and then you still can share those parameters, those weights, but when you do backward propagation, and they'll block you. So those neurons which has been used by previous tasks, you cannot do any back propagation. You cannot modify it. You can use it, but you cannot modify it. So you can see in this case, the forgetting problem is completely solved. It's completely solved. SOUP is another technique which works differently, but the idea is similar. The idea is similar. Essentially, when you learn something and you protect it, okay, protect it. So in this case, we basically have no issue with forgetting. So, but in the TIL, you normally build a model using, let's say, traditional cross entropy to build it. However, that is not good, because we say we need out of distribution detection, right? So in this case, for each of this model we built for this TIL, we use the out of distribution detection model. Okay, so in this case, we use a particular algorithm called CSI, which is pretty strong. So in this case, we have the situation of HAT plus CSI, SOUP plus CSI. And if you see the results, and you notice this green part, the performance improves drastically. And the first data set, M5T, you don't worry about this one. This one doesn't really improve that much because this problem is very, very easy. It's very, very easy. But the other problem for the other data set, you can see we make a major improvement. The margin is pretty large. Okay, margin is pretty large. You can see this C410. This is the C410 data set. The best one was about 62, 60, 64, 66, and we achieved 87, 88. So it's a huge improvement. It's a huge improvement. This are also represent a major improvement. Okay. And so we also have a paper which is going to be published this year, and shows the learnability of CIL. So previous theory just say, we know if you want to achieve good CIL, you must have a good WP, you must have a good TP, but we did not show the CIL is actually learnable. Okay, learnable. So in this case, in this paper, we basically show TIL is learnable. Okay, it's learnable in the sense you can drive the accuracy as high as possible, or drive the error low. Drive to very small, very small. So now let's come to the open world learning. So just now we talked about continual learning. Now we move to open world learning. So we mentioned earlier, the open world continuous learning essentially consists of those two major learning objectives. The first one is we need to learn to detect out of distribution objects. So something you have never seen before, you should detect it. Okay, sometimes we call it reject it, but you need to do this detection, something novel. So for the humans, this essentially is a motivation, right? You detect something new, and you have the curiosity. You want to learn this guy. Okay, you learn this guy. So the second task is to learn this guy. Okay, when you detect this guy, then you learn this guy. Okay, and obviously in this case, after data has been labeled, but in open world, and we don't really have people to engineers to collect a lot of data and get lots of people to label the data. Of course, we can do that. We can do that, but ideally, we want this system to be completely autonomous, And I would say the theory for the CL also applicable here. The reason is also very simple because the theory itself actually unified both, right? The continual learning and this sort of out of distribution detection. Right, so the theory actually applies to both. And if that thing is learnable, of course, in this case, it's learnable, assuming the data are labeled by humans. Okay, but labeling data, that's another issue. Okay, that's another issue which I'm going to discuss. But that's not part of learning. Okay, that's not part of learning. So we want the system to obtain the training data by itself as well, and that's give us a lot more sort of difficulty. So this is the simple version of open world continuous learning. So you can see that this diagram consists of two parts. The blue links, these are those old ones. Those are the old links for just continuous learning or lifelong learning. The orange color ones are the newly added links. So that if you see the bottom ones, we don't have to worry. The bottom ones just say some knowledge we just basically we got from the practical application, then you just go directly into the knowledge base. But we want to we want to focus on those the top two. The first one is the new task. So when you detect the new items, you basically establish a new task. You form a new task that need to be learned. Okay, this is a new thing. I need to learn it. So in order to learn that, you need to get the training data. And then the second link says, I'm going to get some training data, to acquire some training data. And with the task, with the training data, I can learn this new guy incrementally. And then you can see we have a closed loop. Okay, a closed loop. And in this case, when we have a closed loop, then system becomes autonomous. It's possible to become autonomous. Okay. And also this is we learn during application. So it's learning on the job or learning on the fly. So in this case, I give those two examples, two images. One is the self-driving car, another one is the chatbots. So the chatbot is talking to people, and then I have some kind of interactions to learn language, to learn to recognize new objects. So this is the example I often give, and we have this example many years ago, and when we talk about open world learning. This is a greeting bot in the hotel. For example, we have the robots, and which basically roaming around in the hotel lobby and have a small talk with guests. So for example, you see an existing guest, say, hello, John, how are you today? Basically, you can start a small conversation. So this is a very traditional way of doing it. You have a classify, you recognize, take a picture of this person, and then you recognize this is John, and then just start a small conversation. So what happens if you see a guest which I've never seen it before? So of course you need to recognize the person is new or detect this person is new, and which essentially is the out of distribution detection. And at the same time, we need to create a new task to recognize this person. This is the new task. And in order to acquire training data, we need to have some kind of conversation with people. Right? For example, in this case, they say, welcome to our hotel, and what's your name, sir? So you try to get the cross label, right? And then the guest replies says, my name is David. Then you got David is the class label. So next time when you see this person, you can say David. So how do you acquire training data to learn to recognize this David? That's pretty easy. Just take pictures. Of course, if you just take the one profile picture, it may not be good enough. You can, because this robot is sort of it's the mobile robots, and then you can go around and take a picture of this person from a different angle, and then essentially we acquired the training data. And the next one we do continue learning, learn to recognize David. That's CIL, that's class incremental learning, because we have the new class called David we need to learn. Okay. So then in the application, next time when this robot sees David, and then gets, hey, hello David, how are you today? So in this case, the knowledge get accumulated. Okay, and then this robot learn and also become more and more sort of knowledgeable. So this essentially is the process we want the system to achieve in order to become autonomous. So you can see in this case, although that's human involved, but this human involvement is the labeling of the data, everything is completely free, it's very natural. Okay, it's very natural. This is pretty much what we do as a humans, okay, like human. Okay, however, the situation is very complicated, okay, in the hotel, for example. For example, how do you know that object is a person? Okay, it could be an animal, it could be a piece of furniture in the middle of the hallway or middle of the lobby. So if you see that piece of furniture, you won't say, oh, welcome to our hotel and what's your name, sir, right? So that's a problem. So how do you recognize that thing? And how do you know what this guy is? So what is this task? This task is called characterization. So you detect something unseen, sort of new, you need to characterize it in order to respond. Okay, so in this case, you need to respond. How do you respond? You have the characterization. If you know it's a guest, and then you can say, how are you today? And you can say, so welcome to our hotel, our name, sir. But what happens if you see it's an animal? But you don't really know this guy, what this guy is. And then what are you going to do, right? You have to characterize it. You characterize that, yeah, this probably looks like an animal. Then you probably go to report to the hotel employee. If it's a policeman, I probably don't want to do anything. And if you're absolutely sure this guy is a guest, for example, it's a luggage and sort of a lining around, a lining sort of next to this reception desk, then you probably know this person is a new guest. And you can say, welcome to a hotel, and what's your name, sir? So you can see this characterization and adaptation, sometimes we also call it accommodation. It's sort of very important in this open world situation. Okay, and so then you can see this process gets very complicated. Okay, it's very complicated. This blue lines, the links, the blue lines links are those links we have seen in traditional continuing learning, okay, or traditional lifelong learning. Those orange lines, just now we saw only 3 lines, but now you can see there's so many orange lines. So what it means is essentially this process is very complicated. So let's start to see this relevance module. You can see just next to the model, n+1, sub n+1, you see the relevance module. So what this relevance module is doing is just say, when I detect something unexpected, but I want to make sure this is relevant to my performance task. For example, I'm doing a self-driving car, and then if you see something sort of along the street, some people is fighting, you don't really care because that's nothing to do with you, to do with the driving. So that becomes irrelevant. However, if you see something, an sort of unfamiliar object in front of you, in front of you on the road, in the middle of the road or somewhere, which you may hit, and then you have to characterize this thing, and then system need to adapt to the thing. You can't just stop and you don't do anything and just sitting still there. So you need to do something. In order to do something, you need to characterize this thing. You may detect, oh, is this a moving object or is it a still object? And if the guy is moving, you need to detect which direction is moving or what's the speed of moving. So you can adapt yourself to say, if the thing is a still object, is a big object, I probably have to go around. If it's a moving object, it's across the road, and then you just basically say, I can slow down and wait for this guy to cross the road, and then I can move ahead. And this novelty and characterization, we need a novelty characterizer. And the things we are dealing with, unfamiliar situations, very risky. So we need to have a risk assessment. And every step we move, we need to have a risk assessment. Just say, I'm going to take this action, and is this dangerous or not dangerous? Okay, since this is unfamiliar. So adaptive basically says that when you characterize it, and then you need to have a plan of action to accommodate this particular sort of novelty. And then since you need to learn this situation, then you have to communicate with people. So for the self-driving car, we just had that example. When you see something, for example, you don't know what to do, then you can basically ask the human passengers or human engineers say, something in front of them, something I saw, but I don't know what to do with it. And then this human being may say, okay, I just nothing sort of dangerous, just move ahead. So with the images you have taken, you can learn to recognize that small thing, and also you can learn in this kind of situation, you do not have to worry, just go ahead. Okay, so next time you don't have to ask anymore, and then you become more and more knowledgeable. So I think let's come to my conclusion of the summary of this talk. I say continued learning is necessary for intelligence. So the many people asked me several years ago, constantly people, why I was interested in this particular problem. My interest with this problem, partially because of my practice, my sort of experience in the start of a company, which I feel was very necessary to have this kind of capability. But another major thing is just, I think this continued learning is necessary. So you cannot avoid it for any intelligence behavior. All right. So in any intelligence behavior, any intelligence system, you can't really retrain everything whenever you see a new item, right? As humans, we recognize probably millions of, I'm not sure millions, but at least lots of objects. You cannot say anytime I see a new thing, I sort of restart to train my whole head. That's just impossible. Okay, just impossible. And in this case, of course, we try to solve this problem. We have some theoretical study, and then we also show that theoretical study is applicable to open world learning as well. Open world learning, which is very important because we don't really have to reinvent new wheels. Okay. So in this case, the goal, obviously, we want to learn and we want to adapt continuously in the open world by the agent itself in a self-motivated and self-initiated manner. Self-motivation, obviously, that comes from detection, and detect something novel, and give us the motivation to learn, and the self-initiated. We want to learn, we want to acquire data, everything by ourselves, instead of waiting for engineers to give me a lot of training data, those kind of things in order to learn. And that's what we call the learning on the fly or learning on the job. That's pretty much what I want to say. And I have lots of people to thank, and the students, collaborators, and the funders from DARPA, from KDDI and NSF, and also Brahman. This is much earlier, but and all contribute to this work. Thank you very much.
Thank you very much, Professor Bindu. We will have a Q&A session within the panel discussion. So we will move on to next presenters. Three presenters will present various aspects of continual learning. First, Wataru Kumagai, please.
Hello everyone. My name is Wataru Kumagai from the University of Tokyo. I will be presenting under the title, Research as Continual Learning. Please note that this is a talk about what we want to do, so not what we achieved. And to understand the title of my talk, let's consider what researchers do in the research process. So these are the examples of what researchers do in the research process. So for example, when researchers read papers, academic papers, they often come up with a new problem, so a novel problem setting. So we can say that this is kind of a generative task with papers as input and a new problem as output. So this is a generative task, so in the sense of machine learning. And as another example, so when a research problem is fixed, so then researchers try to find the solution. So this can be regarded as also a generative task. So with a research problem as input and the solution as output. And as another example, so when research results are obtained, then the researchers write a paper. So this is also a generative task with research results as input and the paper as output. So we can say that each research task can be regarded as a generative task. In addition, I'd like to explain that so research is also a continual learning task. So research itself is a continual learning task. So first of all, so each paper can be regarded as text data and with figures, so with a few images. And the research topic of each paper corresponds to the class in the sense of continual learning. So then new topics or new classes emerge every day. So please look at the figure on the right. So this is a figure of paper count. So the x-axis means that the publication year of each paper, and y-axis indicates the number of papers. And this red line shows a trend. And please look at this sub-figure in this figure. So this is a log scale version of this figure. So it shows that the trend, so red line seems like a straight line, so in the log scale. So it means that the number of papers, so in machine learning, in the area of machine learning and artificial intelligence, has increased exponentially in recent years. So it means that new topics or new classes emerge rapidly. And then, so since new topics emerge, so the distribution of topics is changing. So that's why, so research itself is a continual learning task. So then, we can have the expectation that generative models with text data can deal with research tasks by using continual learning methods. So related to this, so one notable example is large language models. So large language models are generative models with text data, and they have a vast number of parameters, and they are trained on an extensive amount of text data. And large language models are already used to understand research papers. So includes examples of this includes elicit, so perplexity, or consensus being ChatGPT or something like that. So we can ask scientific questions for large language models. Then the natural question arises here. So can large language models conduct research, so instead of human researcher? However, so this expectation is very difficult to achieve. So that's why large language models tend to struggle with complicated scientific reasoning. In addition to it, large language models also forget the past knowledge after training. So this means that this is a catastrophic forgetting in the sense of continual learning. To overcome such obstacles, we initiated a new project called OTRES. So this is a project on automated research. So we started this project this year, and there are about 30 members in this project now. So this project is expanding rapidly. And the goal of this project, so the goal of this OTRES is make a machine learning model that conducts the whole of the research process. But of course, this goal is extremely hard to achieve, so we set a sub-goal. So the sub-goal is to make a machine learning model that conducts a part of the research process. Okay, to understand the activity of OTRS, let's consider the research process. We think so there are 3 phases in the research process. So that is, so first phase is problem discovery. So researchers find a problem. And then the second phase is problem solving. And after that, the third phase is knowledge sharing. So like paper writing or presentation. Let's look at each phase in more detail. There are some tasks, so there are several tasks in each phases, and these are the examples of tasks in the first phase, so problem discovery. For example, the task use is a main task in the first phase. Task use means that so researchers like us use PC, so especially search engines, so like Google or Bing or something like that. And then researchers can access to the latest papers on archive or for example, to achieve this purpose by using machine learning model, we are planning to train reinforcement learning based model on PC-like environments. And another task is survey. So survey means that so when researchers can access the latest papers, of course, they read the papers. And then, so researchers try to understand the contents of papers. So researchers understand papers. So this is a survey task. So to achieve this by using machine learning models, we have tried to find suitable prompts for large language models to achieve this survey task. The next is tasks in the second phase. So second phase also has several tasks. So for example, the theory. So theory means that so researchers try to prove the theorems and verify proofs and often propose new algorithms. So to achieve this goal, we have tried to find prompts for large language models, and we are planning to train large language models. So far, we found a suitable prompt for large language models, and the prompts achieved a state-of-the-art performance at some data sets for automated theorem proving. Okay, I will skip this part. And so this is the last slide of my talk. So let me summarize the key points of my talk. So first message is that research itself can be regarded as a machine learning task, especially it is a continual generative task with text data. And machine learning models emerged. So machine learning models are generative models with text data. And they are helpful to understand research papers. However, they tend to struggle with scientific reasoning and suffer from catastrophic forgetting. So to accumulate scientific facts with large language models, so there are some obstacles. And to overcome such obstacles, we started a new project called OTRS. So this is a project on automated research. So if you're interested in this project, please visit our homepage. So here, this is the URL of this project. Yes, I will conclude my talk here. Thank you for your attention.
Thank you, Dr. Wataru Kumagai. Next, Dr. Ryokara Keita from AIST, please.
Yes, okay. So, hello everyone, I'm Ryokara Keita from AIST. Today, I'd like to give a short introduction of our analysis on continual learning. Basically, I'm interested in giving some theoretical understanding in complicated and usually high-dimensional learning dynamics appearing in neural networks. And for example, giving some quantitative insight into the appropriate setting of learning algorithms in specific to deep architectures. Or recently, we are more interested in more dynamical aspect of learning algorithms like implicit bias appearing in deep learning algorithms and continual learning. That is today's main topic. And yeah, I think continual learning has very dynamical aspect, and I guess still our understanding is limited in both theory and practice. So let's consider the simplest case. What we considered is continual learning in an over-parameterized linear model. So this is a linear model where the number of parameters is much larger than that of training samples. In this case, there are many global minima, so many solutions, but the gradient dynamics select a specific solution which is equivalent to the so-called kernel-rich distribution given. So this is a trained model, and it is given like this form. And K means, K denotes the kernel matrix, and we refer to this as neural tangent kernel, NTK, because several work reported that under specific limit condition, in a special limit, wide neural networks can find this solution. But I'd like to omit the detail. The important point is model is just an over-parameterized linear model, but the selection of minimum is highly non-trivial. And in this case, by using the gradient descent for the mean square error loss, its solution is characterized by implicitly characterized by the L2 solution. On this solution, several interesting phenomena appears, and one is double descent. So this is a generalization where changes non-monotonically depending on the sample size and the number of parameters. In more realistic training of deep networks, we can also sometimes observe this type of non-monotonic change of test performance. So today's topic is give some insight into the continual learning, give insight into this type of non-trivial change of generalization error appearing in the case of continual learning. This is the framework we used. So recently, some works formulated continual learning in NTK regime, and it is given like this form. I like to the detail, but Fn means a sequentially trained model up to the nth task. So the point is that, so this is an over-parameterized model, so there are many minima. And for example, in the case of training on the second task, its global minimum is given by the richest solution conditioned on its initialization. And its initialization is, in this case, given by the global minimum of the first task. So we can obtain the sequence of global minima. And it becomes, after some straightforward calculations, we obtain this. And today's, what we did is analyzed this model and obtained some insight. And the first one is on the class incremental learning. So this is a special type of continual learning, and each task does not share the same class. So in this case, actually, we can find that there is no knowledge transfer and forgetting. So in this regime, the model gets totally neutral, and there is no positive knowledge transfer and no catastrophic forgetting in this situation. This is because the back-propagated signal in this regime from one head is actually orthogonal with that of the other heads. So I mean the parameter gradient becomes totally independent, and the parameter isolation, so-called parameter isolation, holds. And actually, this is a kind of one limit of wide neural network, and seems to be partially consistent with some empirical observations. Actually, first one says that if we take the large width of the deep neural networks, degree of catastrophic forgetting monotonically decreases, and they also argue that this seems to be caused by the implicit bias of NTK regime in the limit of infinite width. The second work is using a bit different setting, but this work also claimed that if we take a sufficiently large number of parameters in the deep model, the degree of forgetting monotonically decreases. So this means that, taking a kind of large limit of the model, it seems that the catastrophic forgetting spontaneously decreases and forgets less catastrophically. So this is one. First, our insight into the class incremental learning. And the second topic is on the continual learning, where the model can revisit the previous classes in subsequent tasks. This is more close to the online learning scheme. I mean, for example, class Apple is included in the first task, and this class can appear in the subsequent task, for example, in the third task. So in this case, we can obtain more interesting and non-trivial change of generalization error. After using some theoretical tools developed in statistical mechanics, actually we can obtain some analytical expression of generalization error. And I skipped the detail of this slide, but for example, there are two tasks. So the first task A and the subsequent task B. And the similarity of teacher signal, I mean target of the model, is given is characterized by the target similarity. So it is a correlation coefficient between two targets. And for example, we can show that positive forward knowledge transfer appears for sufficiently large target similarities, or catastrophic forgetting of course appears, and it seems to be hard to avoid in the setting of in the naive training of neural based on the gradient descent. But most interesting, I think, most interesting result we obtain is this one. And let's consider the same target function. I mean, the model learns the same function in the previous task and subsequent task. In this case, even in this case, actually, we found that forgetting appears. And it depends on the balance between sample sizes. So for example, in the case of equal sample sizes, just positive knowledge transfer appears. But if the number of samples are unbalanced, like this, so for example, the first task have a sufficiently large training samples size, sufficiently large sample size. In this case, negative backward transfer, I mean forgetting appears, and because now the model runs the same one function, but forgetting appears. So we refer to this phenomena as self-knowledge forgetting, and we also observed this self-knowledge forgetting even appear in more realistic training of deep networks. So if we like this, we divided data set in a random manner, and the first task have a sufficiently large training samples, and in this case, you can see that no monotonic change of generalization error from task to task, because here, so the generalization error increases because of the self-knowledge forgetting. I think, yeah, and I think no time has come, but yeah, this is just, yeah, actually, we can also give some insight by using bias variance decomposition. And actually, the self-knowledge forgetting is caused by the variance term. And in that sense, this is similar to the case of double descent phenomena. But anyway, now time has come, so I'd like to, yeah, finish my talk. So in the simplest case of over-parameterized models, this type of non-monotonic learning appears, and its prediction performance is highly non-trivial, and I think there are still many remaining interesting problems we'd like to challenge. So that's okay. Now time has come, so thank you.
Thank you, Karakida-san. And next, Konishi-san, please.
Sure. Okay, can you see my screen?
Yeah.
Okay, so I'm glad to be here to introduce what we have done through in recent years. I'm Tatsuya from KDDI Research, and I'm currently visiting Professor Bin Liu's group at USC. Okay, I'm gonna talk about two papers that I hope interest you guys. So let me briefly revisit the definition of task incremental learning, TIL. In TIL scenarios, the model have a feature constructor that is shared among several tasks, and each task has its own classification head for estimating the labels. Okay, and in continual learning, the most important objective is called plasticity stability dilemma. Stability issue is to prevent forgetting, and as for plasticity, the models need to encourage knowledge transfer among tasks. As for to evaluate the TIL systems, people usually use the several data sets like CIFAR100 that is split into several tasks, like 10 tasks. And in that, each task has a disjoint set of labels, so that the model needs to prevent forgetting and also encourage knowledge transfer at the same time. For metrics, the common metrics is the average accuracy that evaluate the average performance to current task. And also forgetting ratio that represents how much the model forgets the performance for previous tasks is also used for evaluating the methods. Okay, so let's get started about the introduction of our papers. The first one is the partially relaxed masks, which is abbreviated as PRM. In motivation, we need to introduce a representative method, HAT, called HAT. This HAT prepares the task embeddings inside the model for each layer, and the HAT uses it these task embeddings to determine the importance of neurons in training. So given this the computed importance, the HIT tries to block some parameters feeding to those important neurons and in future tasks. I mean, the HIT blocks the important parameters. So that's why the HIT doesn't happen, doesn't cause forgetting for previous tasks. But as for drawbacks, since the HIT treats all tasks as dissimilar by focusing on preventing forgetting, so this mechanism at the same time discourages knowledge transfer among tasks. To address this issue, CAT has been proposed by comparing tasks one by one to estimate which previous task is similar to current task. And then if the sum of previous tasks are judged as similar, then the corresponding masks of HIT will be relaxed or released. And then the CAT tries to encourage knowledge transfer among tasks. So CAT achieves the better performance in terms of the forgetting also knowledge transfer, but CAT has another drawbacks. I mean, the CAT needs much more computation time to comparing the pair of tasks. So that's why we wanted to develop a new mechanisms that achieves not only forget prevention, knowledge transfer, but also efficiency of learning. Then we proposed the PRM method. The PRM method learning algorithms consist of 2 steps to learn a new task. First step is called dissimilar task detection. For this step, we discovered that the clustering of task embeddings, which proposed in HIT to estimate the neuron's importance, and this clustering can be helpful for estimating task similarity. So given this, the detected set of dissimilar tasks, we move on the next learning with partially relaxed masks phase. In this phase, this method blocks the update of parameters only important only to dissimilar previous tasks. So this method can share the parameters among similar tasks. So by which the model can promote knowledge transfer among tasks well. And through the experiment, we confirmed that this partially relaxed mask technique can achieve better performance with much less computation time against the CAT. And okay, so that's what that is the first papers we've done in recent years. The next one is a more recent paper named the soft masking of parameter level gradient flow, SPG technique. Okay, let me introduce the motivation of our work. So as I said, the HIT tried to block some parameters in training in a task to avoid the forgetting completely. So I mean those such parameter isolation methods try adapt this way of learning. I mean some parameters are fixed for the task, and then we believe that the network will lose its learning capacity if the model learns many tasks. So we believe that the existing continual learning methods has been focusing mainly on forgetting issue, and it has ignored some other important objectives, including knowledge transfer and network capacity for learning a new tasks. So that's why we developed a new technique called SPG. So especially we developed a soft masking technique in this paper. This soft masking technique enables not changing more important parameters to previous tasks much, but at the same time, soft masking keeps all parameters still trainable during the training, even later tasks. So let me briefly introduce how the SPG works. in the first step, after learning some task T, we compute the gradients for all the parameters using a loss function, and then we compute the importance score to each parameters. So then we accumulate the importance. In a sense, this accumulated importance represents the importance to any of previous tasks. And given this accumulated importance, we modify the some update of some parameters. In training task T+1, a new task, we don't do anything in forward pass, but only in the backward pass, we modify some updates of parameter using accumulated importance. This is called soft masking technique. In the other words, the more important parameter will be less updated using this accumulated importance. So these mechanisms gives us two big advantages. The first one is the knowledge transfer. As I said, the existing effective TLL approach like HAT or SUP tries to let each task monopolize a subnetwork in the whole networks. So each task cannot make the full network, can make the most of the full network, which reduces knowledge transfer. But SPG uses the full networks even in the later tasks. So we believe that this technique can encourage knowledge transfer better. And the second one is a more effective knowledge prevention. As you may know, the idea of reducing the change of important parameters has been adapted by existing continuous learning. One of the representative methods is called EWC. It reintroduced another penalty term in a loss function that penalize for changes of important parameters like this. But this way of controlling is doing all parameters together, so which we believe makes it difficult to balance the new task learning and preventing forgetting at the same time. But using our proposed soft masking technique, the SPG can control each parameters with more fine-grained level, by which SPG can enjoy both preventing forgetting and also knowledge transfer at the same time. We can confirm that our SPG can have a better performance in bunch of data sets, even with the many tasks like 100. And also we confirm that our SPG can keep or even increase the network capacity for new tasks. So it can be applicable for many task scenario, many task applications. Okay, I'm wrapping up. So we have been tackling the TIL setup with continuous learning, and we have so far found two findings through research activities. First one is the task embeddings is useful for estimating task similarity that can be used in many continuous learning methods. The second one is the soft masking can achieve the three important objectives. One is the preventing forgetting and knowledge transfer, and finally resolving the capacity problem. Okay, that's all from me. Thank you so much.
Thank you, Koris-san. Now let's move on to the panel discussion. Kumagai-san and Karakita-san, please go up to the stage. First, as a kickoff of the panel discussion, we would like to present a deep continuous learning seminar held in the Dagustu, and Konishi-san attended the meeting, and please make brief summarization in 1 or 2 minutes, please.
Sure. So next page, please. Yeah, as I attended the Dashiru seminar that was held in last March, and yeah, I will give you guys about the brief summary of this seminar. So it was held in the school Dashiru in Germany, and this place is a place in which the people can easily hold the meetings over computer science field. And you can see this website to see how the school Dashiru is organized. And we can see that each meeting is typically held over a week, and the accommodation and the meals are all included in the facility. And I saw that most participants from the European region. Okay, so next page, please. This time Dashiru seminar named the Deep Continual Learning has been organized by Professor Bin Liu and other researchers reading this field of continual learning and also other related research field. And I show the schedule in the right figure, and we can see that the most of the time are used for open discussion, which is in red box. And also we had tutorials and also each participant's presentation for their own recent work. The most attendees from academic institution, including university and some research institutes, but some came from companies like DeepMind and Toyota, Euro, and yeah, like that. So I heard that this kind of seminar will be held again in a few years. So probably some of you guys will be interested in attending that seminar. So next page, please. Okay, this is the last page. So in the open discussion, we had a specific style in which we have split into 3 groups, and in 3 groups, and we had a discussion with in the small room, and talk about a given specific discussion item. And then after the 1 hour discussion, we came back to a bigger room, main room, and exchange ideas what we have discussed in the group. So discussion items are like that, as following like that. So it covers the various items from the settings, evaluation, and also application perspective. So today we would like to pick up some themes from this Dashiru seminar to have a discussion in the next panel session with all the panelists. Okay, that's it from me.
Yeah, thank you, Kori-san. And let's move on to the body of the panel discussion. But due to time limitation, I would like to select 1 question. And we prepared 3 questions. But if you have any questions from your audience, I will pick up this. So please raise your hand if which question do you like to hear in this session. First, what could be promising application of continual learning? If you want to hear this, please raise your hand. No one? Next, what would be relationships between the continual learning and big foundation models? Please raise. Oh, many people raise. And the third question is, what would be the relationships between the continual learning and the online learning? Okay. And last, if you have questions, please raise your hands and give us question. No. So question 2 and question 3 have many people raising your hands. So maybe which one from your view most popular, most people? Maybe question 2. Maybe question 2 is most popular in this in this hall. So we will pick up question 2, and if you want to hear answer of question 3, please please gather after this meeting closes. And so anyway, we will talk about question 2. So the question 2 is what will be the relationships between the continual learning and big foundation models. First, Professor Liu, can you hear? What do you think about this?
Yeah, I think they are orthogonal problems. They are not the same problem. Obviously, we can do continual learning on the large language model or those foundation models, because currently those language models are trained in one session, so they do not train those systems continuously. And in many applications, even in general, we need to train these models continuously because you always have new information, new data, and you want to update this model. And so we want to do continual learning on this large language models or foundation models. And we have been working on this particular problem, and we have a publication this year. And so that's basically two types of things. One is just you continue to train this model itself. Another one is you want to continue to train this model on a specific areas, which maybe you have a domain and this model does not have sufficient knowledge, because some of this is fine-grained data, this large language model might not have seen. So when you have a specific domain, you have a lot of data, and you want to specialize this model, continually pre-train this model on those specialized data, and then you can do that. So in this case, and so there's two issues. One issue is how do you keep the original knowledge? Because the large language model has lots of knowledge that is being trained and contained in the model, and how do you keep this knowledge? And that's essentially what I try to deal with forgetting. And the next thing is how do you adapt this model also to deal with your specific domain? And that's the task we have been working on. And then, of course, in terms of end task, so you can use this large language model as the feature extractor or whatever thing you want to use, and then you want to do a particular end task. For example, you want to classify something, you want to build a dialogue system on this large language model, that's fine too. And for those end tasks, and which uses this large language models, you also can do continual learning as well. Because I mean, not this language model does not really understand everything in the world. So when you have a conversation, sometimes you don't understand what people are saying, and then what it means, the system does not understand what people are saying, and then you can communicate. You can sort of have a dialogue with the person, and then learn what this person is saying. And also another thing is the language model itself has a lot of mistakes. For example, sometimes when you get sort of facts or some reason is wrong, and how do you correct this? How do you edit? How do you fix this model? And that's another continual learning process, because continuously you're going to have information we need to be updated. For example, Joe Biden is president now, but a few years later, maybe somebody else. And then how are you going to change this model, right? How do you modify this model to make sure you have updated information? So you can train this in a large scale. You can also train you can sort of add knowledge piecewise. And these are all very challenging problems, but it's very interesting problems. Okay.
Thank you. Hallucination of the chat GPT, like chat AI, is thought as a big problem. So you think you are
you need to fix those things.
Related to that. Thank you.
For example, I asked a question before about the research topic, and then this guy generates some papers, generate some paper, which is completely non-existent. And those papers are not existent. Those, even the authors are not, never, there was no such authors. There's no such papers. They generate some papers to say, this paper contains some information about that. Yeah. Mm-hmm. So you have to deal with that problem. That's a continual learning issue too.
Yeah. Thank you. Dr. Wataru Kumagai, I have shown your presentation. Is there any other comments or idea about this question?
Rather than comment, I'd like to ask a question about generative model or large language models and the relationship between continual learning and large language models. So Professor Bin Liu, so I'd like to ask a question. So I'd like to make a machine learning model that conduct research, so instead of human researchers. And then maybe we have to find a novel problem. So I think it is a kind of a OOD detection. So a topic, research topic is maybe I think a class in the sense of continual learning, and we have to find a novel topic. And then maybe you have a lot of experience of OOD, so could you give me some comments on in order to find your novel? So novel problem means that novelty and usefulness are both important. So could you give me some comments on that?
Okay. So I think there's two issues. The first issue is novel problem, which sort of might have really existed. So you just basically, as a researcher, you don't know this particular problem, or maybe this problem is not really popular. For example, there are some specific problems which is very interesting, and somebody mentioned that, but largely the community is pretty much nobody knows that problem. And then if the system detect that, and then system can figure out that is very important, very useful, and then I think that will be a novel thing as well. Another thing is the creativity, because a lot of problem is not necessarily something people have mentioned. Sometimes it's because when you connect different things, you sort of create a new problem, and then that problem may be very important to some kind of application. And actually, I can also think of another one is in practice. In practice, you may see some problems, and then you basically based on your knowledge in the past, and based on the let's say this system has read all the papers in Europe, so the SML or the ICRR, and never detect something which is similar to a specific practical problem. And then obviously that will be interesting as a kind of a novelty detection issue, and also out of distribution detection. And then that's a problem probably worth solving, and it'll be interesting to solve. I think it can be seen from these three angles. So it's very rare, and also you create a problem, or you detect something in practice. There's some problem which never been solved by any sort of research papers, for example.
Thank you very much.
Thank you. And Karakita-san is focused. The focus is on the theoretical issue. And
Yes.
Do you have any additional comments on this question?
So first, let me try to give some different perspective. So my interest is basically on more architecture or circuit level of neural networks. And as I mentioned in my talk, recently several researchers in continual learning says that in a large scale, much large scale model, sometimes we can observe the degree of forgetting actually can decrease. So maybe, actually this experiment is based on, just a usual benchmark test on object recognition like CIFAR or ImageNet, and I think much smaller than big foundation model used in natural language processing. But anyway, I think it seems to be interesting to check this type of they actually say orthogonality of representations appear even highly in nonlinear architectures, and maybe I think this is interesting problem, but I guess it can highly depend on the data domain. I mean, image recognition or natural language processing, or maybe it's difference between domain of target or that of source data. And in that sense, I'm very interested in natural language processing have some specific advantage to the continuous learning. I mean, in Kumagai-san and Lin-sensei mentioned that, for example, the text data seems to be helpful to find any novelty of knowledge without any training. I mean, even the situation of zero-shot learning, this type, maybe we can find any novel knowledge from the trained data, and it will be interesting direction.
It is very interesting. The novelty is defined as somewhat multimodal, and so text and image related and helpful to the novelty detection. I think so. And the time is maybe somewhat over, but Konishi-san, can you comment? Can you give comments about this briefly?
Oh, simply saying. So I saw some people got pessimistic when the ChatGPT emerged, but I believe that continuous learning must be essential even with such a big foundation model, in a sense that we need to specify make the model specified to each own the data domain. So like companies will try to sophisticate the model with the data. So if you want to keep the performance for previous tasks, the continuous learning should be still essential, I believe.
Okay. So finally, Professor Bindu, can I ask a final question?
Sure.
What will be next of the open world continuous learning? Can we see open world continuous learning in real world like ChatGPT?
I think it's for a specific application, narrow application, I think it's possible. For example, in the example I give about this robots in the hotel greeting people, I think that is doable. It's not undoable. And you can recognize people and take pictures, have a small talk with people. I mean, if you think about two issues, one is the recognition in terms of image recognition or video recognition, that is doable. I think you can recognize, you can incrementally learn people. I think that's fine. And also in terms of language, so you want to have a small talk with people, and then, for example, you have something you don't understand, you can have a chat with people to understand what he's talking about. I think this is doable, and I pretty much sort of optimistic. I think somebody else try to build a system, and let's try it. I mean, I'm pretty optimistic. I think, of course, in general, it's tough. In general, it's very tough. For example, you go to a terrain. I mean, hotel is fairly limited. Now, if you go to an unseen terrain, goes outside the street, and that's tough. That's very difficult. Yeah. At this moment.
Thank you, Professor. I will dream of such application arrived, and I will continue. we will continue research on this open world continuous learning. And now it's time to close our session. Thank you very much to coming to this企画session, and thank you attending, and thank you presenters. That's all. Thank you very much.
Thank you. We can leave, right?